So I'm not gonna take much time. I'll try to keep it very short and crisp. So I'm Sayak. I'm a deep learning associate at PyImageSearch. I work at the intersection of deep learning and computer vision, and I also work with Lavanya quite extensively to work out reports and stuff. So in this talk, I'm gonna be presenting about TensorFlow Lite and all the cool features that you could use from it to optimize your models, which could be really helpful specifically for production purposes. So yeah, this is little acknowledgement to the ones that really helped me in putting together the slides. So the ideal audience for this short session would be machine learning developers that have worked on image-based models mainly, because the support for model optimization is kind of limited at this stage. But yeah, image-based models would typically work off the shelf. They would work right off the bat in TensorFlow Lite. That's why I specifically mentioned about it. And also this talk would be, I think, very beneficial for the mobile developers looking for ways to plug machine learning models in their applications. Okay, so this is going to be the rough agenda. I'll first be discussing the motivation behind doing on-device machine learning. I'm sure you must be familiar with this, but just to keep it complete. So I'll be also introducing you to TensorFlow Lite in case someone hasn't heard about it, and also different TensorFlow Lite usage scenarios and some of the best practices. And if time permits, we'll do Q&A as well. Okay, so the motivation behind doing on-device machine learning is quite evident, and it has strong reasons. The number one reason being there would be some mission critical applications where batch prediction is not really desirable. You would need to have instantaneous prediction, and that means that your application must be delivering extremely low latencies and close-knit interactions between all the different components that might be involved in your application. And the second point would be not all the regions in the world have good internet connectivity, specifically the developing countries. So how to make machine learning more and more accessible, machine learning products more and more accessible in those areas where network connectivity is still a thing. In those cases, you cannot really host your heavyweight machine learning models on cloud and have them consumed in your application. So in those cases as well, on-device machine learning does make a lot of sense. And thirdly, privacy preserving. This was probably one of the most talked about topics in today's salon. So privacy preserving, you wouldn't, what if you wouldn't want the data to not leave the device where your application is being accessed from? So that's another issue. So that was kind of the three main motivations behind doing on-device machine learning. And yeah, let's just quickly get to the crux or the big elephant of the session. What's TensorFlow Lite? So I'm just gonna read it out from the official statement. TensorFlow Lite is a production-ready cross-platform framework for deploying machine learning on mobile devices and embedded systems. So it has the right amount of tooling, be it for Swift-based applications, be it for Flutter-based applications, be it for native Android-based applications. TensorFlow Lite provides you the right tooling for incorporating machine learning models across different frameworks and platforms, and it also provides you the right amount of tooling for a number of different embedded devices, as you would see later in the talk. So what are all the things that TensorFlow Lite can do for us? First and foremost, it can optimize our models. You would not want to end up your 15 MB mobile application where your machine learning model is of 13 MB size probably. You would want to reduce the size as much as possible, and part of model optimization also means that reducing your model size and also at the same time not letting it affect the performance. And also most of the modern day mobile devices come with GPUs and sophisticated hardware accelerators to improve graphics rendering and stuff like that. So TensorFlow Lite can also take advantages of those hardware accelerators. It also supports HTPU based hardware accelerations and stuff with the use of a concept called delegation, which we'll talk about later in the talk. Different tools, of course, as I mentioned, there are different easy and right tooling methods for integration of machine learning models in both mobile devices and a number of embedded systems, including microcontrollers as well. And yeah, you can find out more using this link below. I'll provide all the necessary links, including the link to this presentation, so that you can refer to when it's needed. So let's discuss some of the different scenarios where TensorFlow Lite can be used. First, I would start with model optimization. So why is it required? I'm sure you might have a motivation behind this, but just to make it consistent and complete. Size reduction. You wouldn't want a 1 GB model in a 1.2 GB mobile application. You definitely want to reduce the size of that model to be able to more production ready and to be able to more and more accessible for a number of different devices. Not all the devices would support running 1.9 GB mobile application. So I hope you got the idea. And when you try to reduce the size of any particular model, it also results in latency reductions and stuff like that, meaning that it would likely take lesser time to run a forward pass with input data along with your model. So that would definitely result in latency reductions and stuff. And it also depends on the size of the model as well, the number of parameters your forward pass is catering to. And also accelerator compatibility. As I mentioned, model optimization can take huge amounts of benefits when the model graphs are being executed on specialized hardware accelerators and stuff. So that's another reason. And there are different optimization options available in TensorFlow. Not the latest ones like rewinding or linear mode connectivity and stuff, but it has all the options that were heavily well studied and well researched upon, like quantization and pruning. We'll mainly be talking about quantization because that's kind of widely supported natively by TensorFlow Lite. Pruning will leave it for another day. So yeah, let's talk about what is quantization. So keep noting down your questions if you may have. I'll try to get to them by the end of this talk. So from a layman's perspective, quantization is nothing but reducing the precision of the numbers used to represent a model's parameters, which is most often done using float 32, although there are float 64 or float 128 based models, but float 32 is the most common one. And by quantization, we essentially mean reducing that numerical precision to a lower one, so that we can represent models parameter using a lower precision based scheme, and it ultimately reduces the size of the overall model. And also there's something called VC complexity, which is used to kind of measure the computational or theoretical complexity of any machine learning model, but we'll not get into that today. As I mentioned, this also results in smaller model sizes and of course faster computation. The lesser number of parameters in your model, the faster the computation would be naturally. And there are two types of quantization mainly. So the first one is post-training quantization, which is natively supported by TensorFlow Lite. There's other one as well, quantization aware training, which is supported by the model optimization toolkit in TensorFlow, by TensorFlow, and it's kind of plays out really well with TensorFlow Lite. I'll share a notebook that would show all of this baking recipes, no worries. And let's talk about post-training quantization for a bit. So post-training quantization happens after a model is trained, not during the model training process. And let's take a very simple example to make things more clear. So just to be sure, this is all in TensorFlow 2.x, and the folks that are familiar with Keras, this would be tremendously helpful for you, I think. So this is a very simple data. So the relationship that we are trying to learn here is y equals to 2x minus 1. Here's how you would define your model. It's a very humble model, nothing very fancy here. Here's how you would train it, all very simple. And here's all the lines of code that's needed to optimize it. So 3 lines of code. Yeah. And I'll talk about these things later in the talk, but the main thing that you need to care about is this optimization option, tf.lite.optimize optimize for size, and that's about it. And in the first line of this block, you are basically asking the TensorFlow Lite converter to load a model that is of Keras model instance type. And in the second line, you are just mentioning what kind of optimization you are looking for, and then you are in the final step, you are just converting the model from a Keras model to a TF-Lite compatible model. And you get a number of different options in the optimizations configuration. You can either optimize for latency, you can either optimize for size, or you can just let TensorFlow Lite decide what kind of optimization that would be best for the given model. And here's how you would serialize the converted model, which is pretty straightforward. Sorry, I missed the opening and closing parentheses, and sorry about that. F.close, there should be an opening and closing parenthesis. So there are different types of post-training quantization recipes available in TensorFlow Lite. So based on your needs of the application, you would want to select a particular strategy. For example, you can see with dynamic range quantization, you would get benefits like size reduction up to 4x, typically 2 to 3x speed up in models inference, and accuracy is kind of retained, but with full integer quantization, accuracy might be dropped off a little, but you would get more speed up benefits and more size reduction and stuff. And on the far right, you can see the kind of hardware compatibility you would get with different post-training quantization techniques as well. So I've linked all of this in the slide itself so that it's easily referable. So as opposed to post-training quantization, in quantization aware training, we trying to compensate for the information loss that would get introduced by quantization. So typically, when you reduce the precision scheme using which the model's parameters would get represented, it would result in information loss and stuff, because you are not precisely denoting all the parameters that your model is learning. So it's bound to incur some information loss and stuff. So in quantization aware training, we try to replicate the kind of information loss that would get introduced with real quantization and stuff. So the idea is pretty crazy, and it's hugely effective. So quantization training aware is absolutely possible with model optimization toolkit, and you can definitely check out this blog to know more about it. And here I can show you the kind of benefits that you can get using quantization aware training. Let me go through the notebook real quick. Okay, it's opened already. So yeah, so in this notebook, I'm using the flowers dataset. I'm also using fine-tuning recipes and stuff. So here you can see the normal model trained using normal fine-tuning takes about 40 seconds to train, and the validation accuracy we are getting, that's about 88.55. And here we are incorporating quantization aware training to make the model aware of the kind of loss that would get introduced if the model would get quantized. And of course the model takes longer to train because the model is still figuring out what's the best way to move this weight in order to best compensate for the information loss that would get induced for quantization. And it takes double time in fact, but the validation accuracy is still higher. And I have kind of executed this across 5 different runs, and I have gotten similar results. So yeah, so here I'm showing you the sizes and stuff, both the models using the normal fine-tuning approach and using the normal fine-tuning, and the quantization training approach, both weighs 35 MBs and 35 MBs. Yeah, as so here I am using post-training quantization to quantize the model trained using quantization aware training. So it weighs 3.3 MB from 35 MB to 3.3 MB, and here I am quantizing the model trained using the normal fine-tuning approach. So its result is far better. Here I am getting 2.9 MB from 35 MB. But let's compare them with respect to accuracies. So I'm running this TensorFlow Lite model through the validation dataset of the flowers data, and here I'm using the quantized model of the model that got trained using quantization aware training. So I'm getting 98.72, which is kind of retained if you take a look at this metric. So we got about 92.91 using the quantization aware training, and when that same model trained using quantization aware training got converted to a real TensorFlow Lite model, we are still able to retain that performance. But when it comes to the quantized version of the model trained using the normal fine-tuning approach, we see that we get 75.09% accuracy, so which is substantially less. So here you can see we can still reduce model size to a great extent without having to compromise on the accuracy side. So I hope that would motivate you to get onboarded with TensorFlow Lite and try out the different recipes that I showed in the notebook. And I think Lavanya will also put up the links to all of this notebook so that you can refer to when it's needed. So a couple of more things. So we saw in the notebook the kind of advantages that we would get using a combination of quantization aware training and post-training quantization. And here are more speed versus accuracy trade-offs, which you could refer to when you are designing your applications as well. And the supported hardware just got increased with time. A closer look at latency. Maybe this would be far more interesting for your use cases and stuff. So here's a floating point MobileNet V2 model without any quantization or optimization. It's being inferred on a single threaded CPU, and the CPU takes 37 milliseconds to run a forward pass on a single input data point. That means a single image. When the model is quantized to fixed point on the same CPU, it takes 13 milliseconds. Using a mobile-based GPU hardware accelerator, using all the OpenCL delicacies that you would get from TensorFlow Lite's GPU delegates, and when the model is converted to float 16 precision, you'd get, the inference is 5 milliseconds and stuff. And using the HTPU USB accelerator, and when the model is quantized to the full integer precision scheme, the inference is 2 milliseconds. So from 37 milliseconds to 2 milliseconds, the journey is quite amazing, I would say. So another TF Lite usage scenario is model maker. So this might be very useful for the folks that do not want to invest in machine learning expertise, but they would want to plug in their own data sets and train custom models without much of machine learning expertise. So here's all the code that one would need in order to train in order to use transfer learning on top of a pre-trained network and use and train an image classifier on the flowers dataset. So you would load the data, you create and retrain the model. Here we are using an efficient net-based model, so that's pretty cool. And here's how you would predict and evaluate the results, and here's how you would convert it to TensorFlow Lite model. Basically, here's how you would optimize the model and serialize it. And let me introduce TensorFlow Lite Model Maker. As you can see, it's a transfer learning library when using TensorFlow Lite. And as I already mentioned, it will be very useful for the folks that do not want to invest in machine learning expertise. So here's all the code that's needed to make use of all of this and stuff. It's 4 lines of code without the inputs. So I have linked a notebook, a fully worked out notebook that you might want to check out for, and feel free to plug your own data sets and let me know if you run into any issues and stuff. And typically the default model is efficientnet Lite 0, the B01, and you can define your own models configuration. It supports ResNet 50 and other models as well, so that should be easy to follow with. And model maker typically works with a limited number of models at this point in time, but more support is coming really soon. As you can see, it already supports BERT, which is pretty cool. I think it would be interesting to see Jack's text attacks that he presented and figure out how to incorporate text attack to train more adversarially robust BERT-based text classifiers and still be able to take advantage of model maker at the same time. So here's where you can find all the pre-trained TensorFlow Lite models, much like the traditional model zoos that you get with TensorFlow or PyTorch. There's a model zoo for TensorFlow Lite models as well. So here's where you can find all of them. And for the folks that are developing mobile applications or that are hacking around embedded and microcontroller based devices, the next set of slides are for you. Yeah, I love Captain America, so yeah. So for the folks that are working in Android, so here's a rough mobile application structure. If you are familiar with Android Studio, this might seem very familiar. So you put your mymodel.tflite, which is basically a tflite model, in the assets folder, and you would also supply all the metadata that would be required in order to consume it using any wrapper class within your application. But with TensorFlow CodeGen tool, you can supply a TensorFlow Lite model to the CodeGen tool, and the CodeGen tool will automatically yield an Android library which is directly consumable using any Android application. So that's cool. So here's how to use the TensorFlow Lite CodeGen tool. Here you are supplying the TensorFlow Lite model, and you are and in the next couple of the command line arguments, you are basically configuring what you would like to call this package, what would be the main class that would be invoked from the application, and where you would like to generate this package. So this is how easy it is. But before TensorFlow Lite CodeGen, you had to put your TensorFlow Lite model in the assets folder, just as I mentioned, and you had to use any wrapper class, any utility class in order to consume that. But with TensorFlow Lite CodeGen tool, you are just getting a library which you can directly use. So yeah, here I have linked a couple of examples which you could refer to and jumpstart your machine learning based applications, and I'll be looking forward to see what you are building with TensorFlow Lite Cavalry. And as you can see, it supports question answering as well and style transfer. So if you were thinking it's only limited to image classification, which is kind of boring maybe, but yeah, you will have to agree, image classification is still one of the predominant use cases widely in the industry that they use. So yeah, it supports question and answering and style transfer based models and a number of different other things. So I encourage you to check out the examples that are linked here. So for the folks that are working with embedded stuff and microcontroller related stuff, here's a list of manufacturers supported by TensorFlow Lite already. ARM is there already, Cadence, Synopsys, and others as well. So TensorFlow Lite is also available for ARM64 based boards, and TensorFlow Lite has a very dedicated build for Raspberry Pi. So if you were thinking how to best optimize your model for Raspberry Pi and other ARM64 based boards, we have got you covered. So yeah. And as I mentioned a while back, TensorFlow Lite is furiously fast if the TensorFlow Lite compatible models are run on HTPU USB accelerators or HTPU compatible boards and stuff. Recently, PyImageSearch released its book called Raspberry Pi for Computer Vision. There we typically, advise all our readers to go for a combination of HTPU USB accelerator and Raspberry Pi for all your embedded systems related stuff, because in our experience we found that combination to work the best. We compared the performance against Jetson Nano and other coprocessor based devices like neural compute stick, but we found the combination of HTPU USB accelerator and a Raspberry Pi typically works right off the bat. So Arduino, so TensorFlow Lite has a dedicated module for Arduino. It in fact has a separate library, but the amount of tooling and the kind of tooling still remains the same. You can use it from the Arduino IDE directly, and there are some sample applications which you might want to refer to if you are interested in using the TensorFlow Lite Arduino library for your Arduino use cases. So there are some best practices. These are the general rules to remember while using TensorFlow Lite based stuff. So if you are willing to use TensorFlow Lite model, first see if there's a pre-trained model, pre-trained TensorFlow Lite model already available that can do the job, because in that way you will save up a lot of resources first and foremost. So there are different state-of-the-art models available for different domains and tasks, as you might have already guessed. So here are all the domains that are which TensorFlow Lite models currently caters to. So as you can see, there are a number of different models across a number of different domains that are already available using all the TensorFlow Lite delicacies that I just demonstrated. So yeah, state-of-the-art NLP for mobile developers, Albert Lite already available, and a quantized version of MobileBert is coming soon. State-of-the-art vision, of course, efficient net Lite, the TensorFlow Lite variant is already available, and on the left you can see the performance is still kind of retained and the latency is much reduced, so that's a good thing. So know your trade-offs and optimize accordingly. You might not want to develop an application where it's very hard to afford the drop in accuracy. As I mentioned, with quantization there might be some drop in the accuracy, but if you are plugging in quantization aware training with the TensorFlow Lite recipes, that might not be the case also. So if accuracy is super duper important for your application, so then you might want to go for separate optimization based options. And yeah, you might want to ask, can accuracy be compensated with speed? In some cases you wouldn't want to do that. So you might want to also draw a balance between speed and accuracy. So always refer to this chart that I mentioned and take the decision accordingly. And use TensorFlow Lite delegates wherever possible. And I think you already are familiar with the concept of delegation, but I'll just read out for the sake of completeness. A TensorFlow Lite delegate is a way to delegate parts or all of your graph execution to another executor. So CPU, your commodity CPU might not be the best one to execute all of the computations that's needed for a forward pass. So in those cases, if you use a specialized hardware accelerator in order to run those computations, you would get tremendous speed ups. So here are all the different delegates that are supported by TensorFlow Lite, and I have also mentioned the kind of precision formats that are supported. So GPU, as all the modern phones come with GPU based hardware accelerators these days. So GPU based delegation is absolutely doable in TensorFlow Lite. TPU, by TPU I mean the HTPU and stuff, in an API is available. This must be very favorite with the Android folks. Hexagon delegates are also available, and also Core ML based delegates for newer iPhones and iPads. Yeah, there's a comprehensive guide on using TensorFlow Lite delegates and stuff, and I encourage you to check them all out. So know more about the kind of support that's provided for your target device, because not all the support are unified. It changes with respect to the target runtime. So it's very important to study the kind of optimized kernels that are supported for your target runtime by the TensorFlow Lite environment. So which precision are they supported, because your target runtime might not support float 16 based optimization. For example, HTTP is all about intake based optimization. So you might want to study the kind of optimized layers that are supported for your target runtime by TensorFlow Lite, and then decide accordingly. So no more here, no more about the performance based practices, which discusses how to open the threads for consuming the TensorFlow Lite models within your applications and stuff. It discusses some other relevant information regarding profiling your TensorFlow Lite based model from Android studios and stuff. So be sure to check it out if you are interested. And if you are looking for a comprehensive set of learning resources for TensorFlow Lite, which I think you should be, because you are getting model based optimizations for free and without having to compensate much on its performance. So I have listed all the relevant links here which you would want to check out maybe. And slides are available here. I'm sure Lavanya must have put all the links in the respective channels. And if you have any questions, feel free to reach out to me. My Twitter is RISING Sayak, Rising Sayak. And if you are interested, I wrote a blog post with weights and biases in the previous week, I guess. So yeah, it discusses a number of different quantization recipes using TensorFlow Lite and the model optimization toolkit. So it's quite comprehensive, and it will help you to get onboarded with these tools and techniques easily. So yeah. So I think we are done, and I'm happy to take questions.
Nice. I love that you can use TF Lite to go from 37 to 2 milliseconds. That's insane to me. That's crazy. We do have a lot of questions. Let's see. So VJ asks, the performance number 2 milliseconds you showed on TPU, what is the image size for that? And is that only inference time, not the transfer of image and results?
Yeah, that's only the inference time, and the image size was 224, 224, 3. That's the standard one for ImageNet based models.
Gotcha. And then Kyle asks, have you worked with object detection models in TF Lite? Have you seen any of these models implemented using mobile nets?
Yeah, so the book that I mentioned, we released from PyImageSearch, the Raspberry Pi for computer vision one. So we used TensorFlow Lite version 1 there. So yeah, object detection based models are typically supported using the version 1, but not by the version 2. The support is coming, as I mentioned in this slide as well. So if you are willing to optimize your object detection based models that are supported, that has compatible optimized layers, you would want to go for version 1. And yeah, we have reduced models from 235 MB to 10 MBs using TensorFlow Lite object detection based models. And typically the models that are supported are the ones like SSD MobileNet or SSD Inception. So that's the kind of object detection models that are supported.
Nice. Boris said, really impressive results. What's the typical maximum model size you can use on mobiles?
I think that depends on the kind of users you are wanting to cater to, and also the kind of accessibility you are wanting to cater to with your applications and stuff. You might not want to deploy your applications on the lower versions of Android mobile phones or iPhones. So it really depends where your application would get used the most, and if you are willing to cater to a broad set of mobile phones, then I would typically recommend a size between 3 MB to 5 MB. But I have seen folks going for more cutting edge stuff. They do not care about the accessibility part, and they are willing to go about up to 15 MBs of models and size. But 15 MB is something that's very typical, and that's also the highest cap that I have seen in the recent days.
Nice. And then Vijay asks, can you please elaborate on the quantization aware training the Keras API? What's the best strategy? And then also you talked about pruning. What does pruning actually do to the trained model?
Yeah. So in quantization aware training, it compensates for the information loss that would get introduced by quantization. So it does so by introducing fake quantization ops in the original model graph and trains the model in a way that is aware of the information loss that would get induced when you would actually quantize the model. So here in this report, in this widths and biases report, I have shown all the different kind of quantization strategy that's available. And if you are, if you are training image classification based models using transfer learning, so here's how you would, define your transfer learning training loop or define your model in the first place. And then it's just 2 lines of code to, instruct your model, hey, train using quantization aware training. So that's all the line of code that's needed.
Thanks.
So yeah.
So the next question, I'm not sure if I'm gonna get this across right, but if I don't, please let me know if I'm wrong.
Wait, is it my question?
No, sorry, not yours.
Okay,
The
sorry.
no, I'm gonna ask yours next. So Jack's like, did I mess up? What type of quantization schema are you using if you're optimizing for size or when you're optimizing for latency? Like int8 POW2, which is the best one for TF Lite?
Again, so if I'm understanding this correctly, you are basically asking what kind of quantization techniques. So it kind of depends, like you might want to refer to this chart to best decide what kind of quantization you would like to go for. Maybe speed is super important for your application, but in some cases, for mission critical applications, accuracy is super important. So it's okay to compensate on the speed part and be able to retain the accuracy part of things. So in integer 8 based quantization techniques, as we can see, there is some accuracy loss, but in my experience, when you are training the model using quantization aware training in the first place and then using post training quantization, then you are still able to retain the accuracy part, as I showed in this notebook, where using a 2.9 using a 3.3 MB model, it's still giving you 92.9% accuracy on the validation set. So it depends on the kind of application and the kind of trade-offs that's super important for your application, and based on that you might want to decide the kind of optimizations or quantization strategies you would want to go.
Nice. And then the last question is coming from Jack. He asks, are there specific tasks for which models are more compressible? Like, for example, is QA question answering better than object detection for model compression?
That's a very good question, in fact. So I haven't done the ablation study. I haven't also seen any paper that does the ablation study as to where model compression is really affecting, if it's task specific and stuff. But I saw in one of the talks, Jonathan Frankel, the lottery ticket hypothesis guy, he actually lamented on how compression ratios actually affects your model performance with respect to a given task. So we can take this offline on Slack, and I will be sure to link you to the talk that I just referred to.
Nice.
Thank you. Awesome.